Thank you very much for the invitation, and I'd like to thank the organizers for organizing this great event and also having me. So today I'm going to talk about mostly the local limit theorem and some joint generalization of mixing in the local limit theorem in an abstract framework, and also applying for certain hyperbolic systems, and then see some consequences of these kind of theorems. This is mostly joint work with Dmitry Dolgopyat. So there is two sections. So the first is about this mixing local limit theorem, definitions, examples, and the second section would be applications, and this is mostly about mixing for infinite measure preserving systems. Okay. So I want to start with something very basic. The local limit theorem for IID random variables. Okay. So you pick IID random variables, zero mean finite variance, you take sums, and then you ask this question, what is the probability that you are in an interval of length bigger 1 at a distance root n? Okay. It turns out you need to distinguish two cases. One is the continuous case. So the continuous case means that the range of the random walk of the random variable is not supported on a lattice. Okay? If that's the case, then you can compute this probability in the following way, that it goes to 0, right? At the speed of 1 over root n. Well, you can easily guess this 1 over root n because in a range of size root n, you are in with probability bigger 1. So in a range of bigger 1, you should get probability 1 over root n. Okay, and the constant is given by Gaussian density, multiplied by the length of this interval, AB. Okay. And there is another case, which is the lattice case. So if your random variable is supported on a lattice, to be a little bit more precise, on a shifted lattice. Okay. So if there is numbers A and B such that x1 takes values on A plus BZ, where B is positive and, well, it could be negative. Anyways, is the biggest such number, then you have a similar expression. The difference, well, there is two differences. One is that you should watch out how you put this V times root n relative to the lattice. So this Vn should be on the lattice, or on the shifted lattice in this case. So Vn is in Na plus Bz, is asymptotic to V times root n. Then you get a similar asymptotics. And another difference is that this measure is no longer a Lebesgue measure, but it's just a counting measure because you're on the lattice. So your set is kind of shifted somewhere else, and you want to count how many lattice points you have in this interval. Okay, be careful. You don't want the endpoints to have positive measure. Okay, so usually what you want to have is that a set whose boundary has measure 0, or you can take text functions. Okay, so these are the two cases that you can have. Now, next topic is LLT for dynamical systems or maps. Okay, so it's the usual setup. You have a, say, metric space. You have a Borel probability measure, and you have a map that preserves your Borel probability measure, T. And then you take these partial sums, the Birkhoff sums, Sn of f, where f is an observable. Say I put here Rg. Previous example was R, now it's Rg. And now I want to introduce this definition of a local limit theorem. So this, the map T and the observable f as a pair satisfies the local limit theorem if there is a closed subgroup. In the previous examples it was, either Z or R. Now it is in higher dimensions, so it could be a product of lattices and Euclidean spaces. So if there is a group M and a translation, so that's something very similar to the previous statement holds, that if you pick a test function, well, I know I picked the test function instead of intervals, is Z is denoted by Z, where Z, or Z is, no, this is a typo, I'm sorry, so this wants to be a U. So Z as is a continuous and compactly supported test function that you evaluate, and that decays n to the wait, this is negative d halves, another typo, so sorry. This is n to the negative d halves Gaussian density, and the measure, so the integral of this test function with respect to the Haar measure on this group. Okay, so this is the LLT, this is what I'm going to call an LLT, and then there is this mixing LLT, which is the joint generalization of mixing and LLT. So I just put in some red terms. So if you forget about everything black, then you get mixing, right? So the red part here is mixing. And if you combine the two together, then you get a mixing LLT, which I call MLLT. Good. So I'll give examples, but first I develop a little bit an abstract framework. So for dynamical systems, there is always this little bit of issue with coboundaries. Okay, we already heard this in previous talks, so let me just go through it very quickly. If you have two functions, g and f, so as g minus f is a coboundary, so that this equation holds, then Sn of g is almost the same thing as Sn of f, except for these two are minus g plus h composed with t to the n. So that being said, if you have LLT for g, then you have something like an LLT for f. So actually, what is true is that if Tg satisfies the MLLT, then Tf also satisfies a kind of MLLT, but not exactly the same definition that I wrote on the board, because you no longer have a product measure, but instead you need to apply convolution by age and negative age. Okay, so the formula becomes more complicated, so I'm not going to put down the formula, but it's kind of something like a very similar statement, except that here you no longer have a product measure, but you need to apply convolution with age and negative age. Okay, good. So next thing I would like to study is flows. Okay, so far I've been talking about maps. So a very natural class of flows is the special flow, suspension flow. Okay, so what is a suspension flow? Or even better to say suspension semiflow. So you have this x in the base and the map t as before, and you put a roof function on top, which I denote by tau is bounded away from 0 and is, say, square integrable. It doesn't have to be bounded from above. On the picture it's bounded above. And then you have the special flow that you pick a point x and you flow with a constant speed straight up until you reach the roof. And when you reach the roof, then you immediately come back to the bottom and you apply t in the base. And you keep flying straight up. That's called a suspension flow, a suspension semiflow, if t is non-invariable. And it preserves an invariant measure, which is just the invariant measure in the base times Lebesgue in the fiber. And maybe I just normalize to get a probability measure. Okay, so here is a theorem. This is kind of the simplest theorem that I wanted to start with. But somehow the proof is very similar to the proof of the forthcoming theorems. I'm not going to discuss proofs, but maybe I say a few words about it. So the idea behind this theorem is that you want to lift the mixing local limit theorem for maps to flows. Okay, and usually you need to drop the dimension by 1. So what I mean by that, if you have a one-dimensional mixing local limit theorem in the base, like tau is an observable, a one-dimensional observable, that's a one-dimensional mixing local limit theorem in the base, then you can lift it up for a mixing local limit theorem for the flow, but you get a zero-dimensional, that's just mixing. Okay, so this is the theorem. If t and tau as an observable satisfies the mixing local limit theorem, then what I really want to say is that GT is mixing. Okay, of course I need more conditions. Okay, so there is a technical condition which I'm not going to define precisely. I would just say certain moderate deviation estimates need to hold. Okay, if that's true, then GT is mixing if and only if GT is weakly mixing, if and only if you have this characterization that the minimal group is R. Okay, so record that I introduced the minimal shifted group. So there is a group M and the shift R. Okay, So the minimal group is just the group generated by M and R, but these groups are always closed. So I'm always considering closed groups, so I need to take a closure. Okay. If this is equal to R, then you have mixing, and that's an if and only if statement. One direction is super easy. If this is not equal to R, then it has to be a lattice. If it is a lattice, then practically speaking, what happens is that your tau can only take values in a lattice. Of course, that's not mixing, right? So the only time when you can come back to the base is given by a lattice. But that's not mixing. That suspension flow is not mixing. Okay, you need a little bit extra work here because of these co-boundary terms, but that's morally the story. Okay, the other direction is harder. And in order to prove the other direction, what we do is that we consider, well, that's a very, very common idea. It's not really a new idea. People have been doing this for many years. You consider the number of returns to the base before a given continuous time t. Okay, say it's n. N is an integer, usually. N is integer and t is continuous. So if this n is typical, typical means it's 1 over, typical means that. What would be the typical number of returns to the base? That would be 1 over nu tau times t plus or minus some big constant times nu t. If n is in this interval, then you just use the local limit theorem, the mixing local limit theorem. Okay. There is an extra piece of difficulty that sometimes n is not in this interval, and there is a big number of such n's for which it is not enough to consider the mixing local limit theorem, and that's why we need a little bit of extra assumption, and this is what the moderate deviation kind of estimate is used for. Okay. Yeah, that's a very simple proof, and next thing is to take it to one more dimension. So as I would want to consider two-dimensional MLLT in the base, and consequently one-dimensional MLLT in the for the flow. So that would be a local limit theorem for the flow. Well, I didn't tell you what is a local limit theorem for a flow. There is a long definition, a complicated formula, but morally speaking, what you have to do is go back to the definition for the map and replace discrete time with continuous. Okay? So what you have to do is that you have a suspension flow, which I denoted by GT. Okay? You have an observable now on the phase space of the flow. And what you need to do is that you replace the Birkhoff sum by this integral. Okay? And then M hat R hat are the group and the translation. And here's the next theorem, which is very much similar to theorem 1, except that, as I said, is one higher dimensional. And theorem says the following, that assume this a two-dimensional observable satisfies the MLLT, where the two-dimensional, so the first coordinate is, you had this observable on the phase space of the flow, so you project it down to the base, so you just integrate along fibers, and you get an observable in the base. That's the first coordinate, and the second coordinate is tau. Okay. Assume this satisfies the MLLT with the group M and the translation R. Assume also these kind of moderate deviation estimates, which I never formulate precisely, but it's not very painful. Okay. Assume furthermore that GT is mixing. If it is not mixing, then it's not really LLT for a flow. It's more like LLT for a map. So, and I don't want to consider that case, and some regularity conditions on alpha. Then the statement is the following: that GT alpha is satisfies the MLLT if and only if this minimal group is somehow nice. Okay. So I want to refer back to the very first slide. I told you that for maps, you can have two kinds of LLT, either continuous or lattice. Okay. Now for flows, lives become harder. I would say for maps, the lattice case would be like an arithmetic obstruction for the continuous LLT to kick in. Okay. Now in this case, there are more arithmetic obstructions, and the more arithmetic obstructions are formulated in terms of this pair of observables. Okay. So if this minimal group is R squared or Z times R or a sheared Z times R, then you're fine. And in general, you could have a two-dimensional lattice. That's not fine. Okay. So remarks in case 1 is the nicest case. You don't need co-boundary terms, and M hat is equal to 1. In case 2, a little bit less nice a case, m hat is, of course, a lattice. R hat is still 0, but you do need coboundary terms. Okay, so for simplicity, for the sake of this lecture, I assume that this pair satisfies the MLLT, the regular MLLT, no coboundary terms. Even though I assume that, I still need coboundary terms for the flow. Okay, that's how it is. And case 3 would be, well, still you need coboundary terms, m hat is still a lattice, but now you need R as well, or probably should be an R hat. So that kind of R hat is a shear that transforms this picture into that picture. Okay, that's the moral of the story. Maybe I want to a little bit comment on this extra arithmetic obstruction. So in case this is a lattice, then we have convergence along subsequences. Okay, what do I mean by lattice? So could it be Z2? Could it be Z2? I wanted to, well, there's a lot of things on the board, right? So I wanted you to remember this condition, that GT is mixing. So if GT is mixing, then according to Theorem 1, the projection of this group to the second coordinate needs to be dense. Okay? So it can't be Z2, but it could be a general two-dimensional lattice. Okay, so I'm showing you an example. Actually, the example is very simple. You don't need to know anything about dynamical systems. It's an IID example. It's just an arithmetic thing. So look at an IID case. Okay, x and tau is a two-dimensional random variable which is supported on these 3 points uniform distribution. Okay, so z1, z2, z3 are 3 points. You have a uniform distribution of 3 points, right? It couldn't be simpler than that. Now these 3 points are chosen in such a way that the lattice that they generate projects down to z in the first coordinate and projects down to a dense subset in the second coordinate. So the closure would be R. Okay. And then you want to consider something IID, but I think it's called a renewal reward process. Instead of putting down formulas, I show you a video. So this needs to be a continuous time system. So basically what happens, well, I should comment on that. So green line is vertical line is the continuous time, so green is going with constant speed, and each time you are at the blue point, your random walker is at the blue point, then it picks one of the 3, either Z1, Z2, Z3, with probability 1/3, 1/3, 1/3, and it will jump to that point as soon as the green line reaches that point, okay? So it jumped to this point when the green line got there. So let's see where it goes next. Oh, it didn't go to the right. Oh, it didn't go to the left. Wait a sec. I know for certain that it has to go there, right? I just have to wait until it gets there because it can only go to 3 places. Indeed, it got there. Well, you're lucky. And let's see where it goes next. Oh, it goes there. Okay, well, the video ends here, so that's the end of the story. So this is called a renewal reward process. Basically, what is a renewal reward process is that you look at the first coordinate at continuous time t. Okay? And this fits into the framework of what I said before. It's a suspension over a Bernoulli shift. So it makes sense to ask the MLLT, and I just tried to explain why the MLLT fails in this case. So I need to zoom out, right, because I need to consider a large t, and I need to draw this picture, but then I need to zoom in because this picture is small. So basically what happens is that you pick a large t, okay, so this is t, for instance, t is an integer, and you want to ask what is the probability that at continuous time t, your position is at 0, right, because it projects down to a lattice, so your position is at exactly 0, it's a lattice. Now the trick is that, well, the probability of reaching all of these red dots is approximately the same. It's a constant over root t, okay? So for instance, the probability of getting here is a constant over root t. Now if your t is here, then the way you can get here is that you got here and then you stayed. So that's a constant over root t. But if you pick your t from here, or even better here, then the only way you can get here is that you got here and you didn't jump neither to the left nor to the right. You need to jump up. So the probability here would be 1/3 of the probability here. Okay, so there is no convergence as you multiply by root t. But instead you have convergence along subsequences when the subsequence is given by just take t mod 1 and ask whether it falls into this interval or that interval or the third interval. Okay? So you have something almost like a local limit theorem, but you need to pick subsequences. And we have a formula for that. I'm not going to show you the formula because it's ugly. But it's not very difficult. I'm just telling you there is an extra arithmetic obstruction for the limit theorem to, for the local limit theorem to hold. Okay, I'm kind of going slow. Anyways, so far this has been kind of abstract, and I didn't really get my hands dirty because I told you that I am assuming I have an MLLT in the base, and then I derive some consequences. But come on, how do I prove the MLLT in the base, right? That's something highly non-trivial. So I should really go and show you examples that where these kind of things work. So MLLT in the base for maps, there is a lot of literature on that. There's a lot of papers. I'm just mentioning 4 kind of versions of MLLT, not exactly this, not all exactly the same way as I said, but roughly speaking. So it's kind of an early paper, Guillaume RD, for unsolved diffeomorphisms. And there is this paper by Aronson and Denker for Gibbs-Markov maps. So actually, they say the Gaussian case is easy. So they consider the non-Gaussian case, right? So obviously you can extend the LLT for these kind of alpha-stable distributions. Domo and Thomas Royu have a paper on certain Young towers. They use this kind of Fourier method for a tower, so they need to make sure that the tower has exponential tails and basically fits into the framework of the first paper of Lysan. And then Sebastian has another paper on general Young towers. So all these kind of versions of the MLLT for base map. There is many more. Okay, this is not a complete list. Okay, if you have some results and your name is not on this list, then don't be offended. I know there is many more. I'm not going a complete review. So, okay, we have this. We have these kind of results in the base. So, could we kind of use some of these to infer MLLT for suspension flows? Okay, and we kind of can, but it gets a little bit technical. So, maybe please allow me to for 3 minutes to talk to experts. Okay, so what we do is that we consider a suspension flow over a Young tower and Hölder observables, and I claim that the conditions of Theorem 2 are satisfied. Well, there is 2 things to it. So one thing is that actually when we consider suspension over a Young tower, but we don't really use results for Young towers. What we do instead is we more like using Aronson and Denker. Because if you have a suspension over a Young tower, well, actually the Young tower is already a suspension. It's a discrete suspension, right? So what we do is that we consider the first return to the base of the Young tower, that's a Gibbs-Markov map, and we look at it as a suspension over a Gibbs-Markov map. So morally speaking, it's like Aronson-Denker, but it's not just the LLT, but we also need to check these moderate deviation kind of bounds, which actually, for certain domains, we use a paper of in Melbourne, and for other domains, which are almost typical ends, so we're close to this k times root t, what we do is a very weak version of the error term estimate for the LLT in the base map, in the framework of, say, Aronson-Denker. Okay, so there are these technical difficulties. Anyways, assume we get that, and we do get that. And there is an extra piece of difficulty, okay? So usually you don't really care about suspensions over Young towers. What you care about is like examples, like physical systems that have a Young tower representation, okay? So assume you have we have these examples. There's a list here, for instance, Sinai billiards, or well, for XMA flows you can do actually better than Young tower. So LSV maps, Liveran is also YMT maps with kind of a finite measure, geometric Lorentz attractors anyways. So there are a couple of examples. So usually what you want to do is that you want to pick your example and you want to prove the LLT for that. But if you go to the tower then, and you prove the LLT for the tower, it's not so obvious to come back because say you get a co-boundary term on the tower. So does it correspond to a function in the, for the original map? It's not obvious, right? Or if you actually, there is some extra difficulty with observable being bounded. So, sorry, not bounded. Observable being compactly supported. If you have a compactly supported observable in your original map, You lift it to the tower, it's not necessarily compactly supported. So there are these difficulties. In some cases we can overcome these difficulties, but it's getting kind of technical, and in some cases we can't. For these cases we have some version of the MLLT for these examples. For axiom A we can do more than just SRB measure, we can do this kind of Gibbs measures. Okay, any questions so far? Okay, so I'm about half time, and it's time to start section 2, I guess. So section 2 is about, I would say, certain applications, okay, of the kind of ideas that we have been discussing. But these kind of applications, I think, are very interesting on their own. So it's not just application, it's like kind of like connections to other questions. So first thing is kind of a very simple generalization of what I said before, and that would be just the case of how to go from map to the flow when your roof function is unbounded, maybe not even integrable. So, if so this is the setup here. So you have a suspension flow, but your roof function this time is not just unbounded, but in fact is non-integrable. Okay. So that being said, you can still define this invariant measure. It's an invariant measure, but it's an infinite invariant measure. You can't normalize it because it's infinite. So you have a suspension flow which preserves a natural, physical, infinite, or sigma finite invariant measure. Okay, so what can you say? Well, here is a theorem. And the kind of ideas that I explained to you extend to this setup. Okay. You just want to count the number of times you return to the base before time t. Well, it's not going to be this thing, it's going to be something else, depending on your alpha. It will be something like a domain of attraction of an alpha stable low. But anyways, if you have an LLT for the base map, and you have certain version of the moderate deviation estimate, then you can conclude LLT for the flow. Well, let's just do it for the simplest case, the dimension 1 in the base, dimension 0 for the flow, so that will be mixing for the flow. But there is substantial differences, okay? So first I assume it's, this polynomial tail. Well, actually, we consider slowly varying as well, but I just ignore this for the sake of this talk, okay? So assume it's polynomial with alpha between 0 and 1. Assume furthermore that T tau satisfies a stable version of the MLLT with some alpha, well, that's the alpha, right? And some moderate deviation estimates. Then what you're gonna get is, well, this time it really matters a lot what kind of test functions you pick. And for instance, the test functions that I could pick is almost everywhere continuous and compactly supported, at least on the fiber, anyways. So for instance, there is a finite M such that they are supported on the space S less than n. Okay, then what's going to happen is that, well, this thing needs to go to 0 because it's an infinite measure preserving system, and I'm just only looking at finite measure, like maybe even compact finite measure subspaces. So this thing goes to 0. Well, there are many experts in the audience who know this very well. But there is a version of the mixing, and that says that this will be given approximately by the product of the invariant measure of f and g, and there is a scaling, okay? And the scaling in this case is t to the alpha minus 1, where the alpha is given here. This is sometimes called the Krickeberg or Krickeberg-Hopf mixing. And the condition is very similar to the previous ones, that the minimal group needs to be R. Okay, so in case it is a lattice, it's obvious that you can't have mixing. And this is an if and only if statement, so if it is not a lattice, then you have mixing. There are many results on kind of speed of mixing. So for instance, if you have two periodic orbits whose ratio is irrational, then this is sufficient for mixing. But it is kind of well known that it could be slowly mixing unless this number is very irrational, right? So if this ratio is Diophantine, then you can usually say more. But here we can say less, but at least it is an if and only if statement, right? So I want to tell you maybe a kind of limitation of this theorem, okay? So the limitation would be in case alpha is less than a half. So what is going to happen for alpha less than a half? Let's think for a second. So here, this thing is actually going to be less than that thing. So t to the alpha minus 1 is less than t to the negative alpha. So I have certain estimate on the tail, and I want to prove something stronger. I want to prove something that goes to 0 faster than what I have the estimate on the tail. There's no way I could do that, right? For instance, if tau has atoms, the distribution of tau has atoms, then that kind of tells you that for certain t's, you could have something like t to the negative alpha, and there is absolutely no way I could mix with this pate, because if I haven't come back to the base, there's no ways I could have mixed. Okay, so this is explained here. So if alpha is between 0 and a half, then t to the negative alpha is bigger than t to the alpha minus 1. So only assuming this condition that we put here, there is no reasonable system that satisfies the conditions, not even IID, okay? So this, for the IID setup, this has been studied quite extensively. So there is a paper by Garcia and Lamperti. I think for IID they call it strong renewal theorem. And Garcia and Lamperti kind of found this problem. And there was a kind of an open problem to find equivalent characterizations for like if and only if conditions for the strong renewal theorem to hold. And there is a very recent result by Caravan and Doni for the IID, where they found the necessary and sufficient conditions for IID in the case alpha between 0 and 1/2. So one thing that you could do is you assume it has a density, say the distribution of nu has a density. Okay, then this would hold, but that's, it's sufficient but not necessary. So the necessary and sufficient condition is harder to find. Anyways, this problem has been settled, at least for the IID case. And I also want to tell you there is a very similar results by Ian and Dahlia. Well, I mean, similar to this theorem 4. Oh, wait, what happens now? Okay. So is a very recent result. Maybe one difference is that they have some other conditions. Well, the MLLT follows from their conditions, but instead of the moderate deviation estimate, they have some other conditions, and well, they have the same conclusions, and they can in particular apply their result for other kind of maps. Well, not exactly the same kind of maps that we can apply for. Anyway, so here is an example. I need to show you examples, right? The abstract setup is good, but if I can't show any example, then it's kind of useless, right? So this example is kind of a popular example, right? It's the liver and isosceles map. I didn't put down the formula, but if you listened carefully in previous lectures, then you hopefully still remember because it was already used. Okay, so there is a parameter, I think in the liver and isosceles paper is denoted by alpha, but my alpha is kind of taken already. So I denote it by R, and you can tune this parameter, and depending on how big is your R, you can either have a finite absolutely continuous invariant measure, or you can have an infinite absolutely continuous invariant measure that the density blows up near 0. So the measure of any interval epsilon to 1 is finite. Okay, so I'm considering this case when the measure actually so I'm talking about a map. Okay, so the invariant measure for a map, natural absolutely continuous invariant measure for a map, is already infinite. Okay. And then I'm considering a suspension over this map, and my roof function is going to be piecewise Hölder. Okay. And I'm claiming the following: if tau tilde is not cohomologous to a function supported on a lattice, then the Krickeberg mixing holds for functions f and g whose support is bounded away from 0. Okay, so the integral of f and g in particular is finite because I told you that the measure is finite for any of the interval epsilon 1. So for any epsilon, it's a finite measure. So these functions are integrable. And yeah, so the Krickeberg mixing would hold. If and wait, so I didn't put it if and, but this is an if and only if statement. So yeah, if it is cohomologous to a function that is supported in a lattice, then the mixing doesn't hold. So there is, you know, a non-trivial step when you wanna derive this example from the theorem that I showed you before, and this is kind of similar to the difficulties that I explained before. That if you have if you want to induce and you consider a suspension for the induced system, then it's not so obvious to go back. So for instance here, the way you want to use this theorem is that you induce, right? So you consider a set of finite measure, which is a Markov example. So a natural example would be 1/2 to 1/2 to 1, and then you consider the first return. So you induce, okay? And that is a that's an inducing scheme, and then you have a corresponding tau, which in this case is going to be now unbounded. So for that induced system, it fits into the framework of this Theorem 4, and you can apply Theorem 4, and then you need to make sure that you can come back to the original system. That's a non-trivial piece of argument, but in this example it can be done. Okay, so yeah, so we have an example. That's basically all the examples that we have, or well, you could do other Gibbs Markov or whatever certain Markov properties. In fact, I also want to discuss some other versions of mixing, some other definitions of mixing. So in case of infinite measure-preserving systems, you know, nothing is easy. You cannot, well, maybe ergodicity is easy, but nothing else is easy, not even the definitions, not even the level of the definitions. So I showed you this Krickeberg mixing, but that's not the only definition that you could consider. And in fact, there are some definitions by Marco Lenci, which I think are quite interesting. And basically what he says is that the Krickeberg mixing focuses on a compact or a finite measure part of the phase space. So it basically tells you what happens in a finite measure chunk of the phase space, and it doesn't really tell you much. Well, implicitly it does, but doesn't really explicitly tell you a lot about what happens far apart. And in statistical physics, what people consider is, well, they don't really have infinite measure. What they have is a measure in a big box, and then they let this big box go to infinity. So the proposal of Marco is more or less the following, okay? This is not going to be very precise. No, sorry. So consider a map which preserves an infinite invariant measure nu, and fix a set of bounded test functions, which I'm going to denote by Bohr G. Well, I'm not defining it very precisely. Later I'll give you a more precise definition. But at least what I want is that averages over big boxes converge. Okay. So if you let the measure, oh well, that's a nu, sorry. So if you let the measure of V go to infinity and you average over this big box, then this limit exists. Well, that's a bare minimum that you want. Well, there is usually more requirement than this. Okay. So you have a collection of functions which kind of have average values over large boxes. And then you can ask these kind of questions. Can you talk about mixing of these global observables? So there is two definitions which are kind of related, but not exactly the same. There is a local global mixing and a global global mixing. So local global mixing would be, you start from a localized function, say L1, okay? So lowercase phi is L1. And then you pick a capital phi as an observable after a big number of iterations. And capital phi is a global function, okay? So what is going to happen in the limit? Well, in the limit you get this kind of product, so it's kind of a mixing statement. Okay, and if this is true, then you call it local global mixing. Global global mixing is when you start from a global observable and you want to evaluate a global observable at time capital N. Okay, so well, you need some normalization here because otherwise this measure will go to infinity. So you just normalize by the measure of the box, and you let the measure go to infinity and then N go to infinity. And if you want a precise definition, then you can either put your lim inf and lim sup. You require that both of these converge. If both with lim inf and lim sup converge, then you call it a global global mixing. Okay. So I want to show you the simplest example and then proceed to less obvious examples. Okay. So the simplest example is called the Z extension or ZD extension. Say you have a nice locally compact metric space, okay? And or it could be even compact. Anyways, it's not very important at this point. And you take product with ZD. Okay. So on this space X, you consider a skew product map. Okay. So in the base, you just apply an F, which is a self-map of M. And in the fiber, you add T of Z is equal to Z plus kappa Y. Okay? So the F in the base map preserves a invariant measure nu 0. Okay? So you can extend the measure, so you can consider this natural induced invariant measure for the extension, which is just nu 0 times counting measure. It's obviously infinite. Right? That's a natural infinite invariant measure for the map, which map T. Okay, it's just a remark to connect with previous topics that if you have an MLLT for F and kappa, that implies that T, capital T, is Krickeberg mixing. Okay, so the MLLT basically, you just have to apply the MLLT with Z equals 0. So you count the probability of coming back. That is given by, say, 1 over root n. That will be the scaling in your Krickeberg mixing. And the mixing part of MLLT, the M part of it, is actually giving you this mixing. So that's kind of a connection. But there is more to it. It's not just this remark. So now I want to study these global mixing properties. So I consider two choices of observable classes of global functions. So there is G0 and GU, and I want to be a little bit more precise with my definitions, okay? So recall the idea is that the averages need to exist, so the limit of the averages need to exist as you average over big boxes. So in case of GU, I consider a set of bounded uniformly continuous functions, okay, whose averages over boxes containing the origin converge, okay? And the other thing, the GU, so the 0 stands for the fact that you always average over boxes that contain the origin. GU is a uniform thing that so for given epsilon, you can always find an L, such that if your box is bigger than L, then over this box, the average is closer to the limit than epsilon, no matter where this box is. Okay, so the location is uniform. You can put it anywhere you want. Okay, so obviously GU is a more strict requirement, so consequently the set or the class GU is smaller than GU. Okay, so far so good. We have XZD extensions. We have specific choices for global observables G0 and GU. So maybe let's look at some results. So there is a theorem, Theorem 5, if I count correctly, that says that in the case of Z extensions, did I say that? I think I did, yeah. Yeah, so basically so this is the setup, okay? This is Z extension or ZD extension. If this guy satisfies the MLLT, then both local global and global mixing hold for both of these GO and GU. Well, actually, it's enough to put here GO because GU is a subset of that. Wait, I didn't tell you anything about the group. Should I have told you something about the group? No? Yes? Well, this is a Z extension, right? So kappa takes values in the integers. So it needs to be a discrete group. It can't be continuous, right? So kappa, so the second coordinate is an integer or ZD, okay? So it's discrete anyways. It could be, a finite index subset of Z, but that will not make a big difference. Okay? So this is the first result, and basically it tells you that the mixing local limit theorem is also useful for deriving these kind of global mixing results. Okay? But actually we can extend it. Well, okay, so here's an example, Lorentz gas. Many of you know it's my favorite example. And it was defined yesterday, so maybe I don't have to define. Well, that's a periodic, I should say periodic Lorentz gas. Okay, so that fits into this framework. Now here is the extension of this result to systems that are not Z extensions, not periodic, but kind of almost. So if you have a system which satisfies the MLLT, okay? Maybe I should have emphasized this earlier, that the MLLT is a, a very strict assumption, a very serious assumption, and usually the only examples when MLLT you can verify for the map involves some amount of hyperbolicity. Okay, so hyperbolicity shows up in my title, but I talked about it kind of little. There is always some sort of hyperbolicity implicitly, because otherwise there's not a lot of chance that you could have an MLLT. So assume you have for instance, a hyperbolic system that preserves a natural infinite invariant measure. It's not a Z extension, but somehow it's close to a Z extension. Okay? Then I claim that we can check under certain assumptions global, and local mixing. Now the assumptions become quite technical, so I'm not going to tell you what are those. Instead, I'm just saying if T tilde is very well approximated by T, okay, then T is global mixing with respect to GU, then so is T tilde, okay? So if T is global mixing with respect to GU, well, I can't do it for GO, I can only do it for GU, okay? And this guy is very close to, T tilde is very close to T, then you can extend the global mixing to T tilde. And there is a more restrictive definition of what do you mean by very well approximated. You have more technical conditions, which is just well approximated, and then you can extend the local global mixing as well. It's kind of harder to extend the local global mixing. Okay, so you need more conditions, but then you can do it. So maybe I have to show you examples. And how much time do I have? 5 minutes. 5 minutes, okay. So here are the examples. There's a lot of them. So the way you want to read this, well, how do you want to read this? That's a good question. If you know what these systems mean, then you can read your favorite line. So basically we have these examples, which are all physical systems. So all of these systems are motion of some hard balls subject to either scatterers, like in the Lorentz gas, or some external fields, like in ping-pong models, or both scatterers and external fields, like in this example too. And well, the locally perturbed Lorentz gas just means that you have a periodic Lorentz gas and finitely many scatterers you replace by something else. But that something else needs to be sufficiently regular, like boundaries 2, 3, 3, and strictly convex. Okay, finitely many pieces. So this is a local perturbation. So there is always a reference here for the well, maybe not the first, but an important reference for these systems. But these references don't study local global mixing. Okay, these define the map. So for instance, the local perturbation is studied by a map by studied in a paper by Dolgopyat, Sass, and Mariu. And so in this case, we have global mixing for both map and flow, and local global mixing for both map and flow with respect to the big space, GO. Okay, so this is kind of the nicest example in the sense that we can prove the most, or actually the most is true. Well, I didn't really talk about flows, but you can extend the definitions from map to flows, and you can talk about local global and global mixing for flows, okay? There is a natural map, and there is a flow, where billiard is defined as a flow, and there is a natural map. So in this case, it holds for both. So what happens in case of potential fields? Well, the potential field means that, well, you know what it means is, so the motion of the particle on a Sinai billiard table or a periodic Lorentz gas is subject to an extra potential. And so if the potential is asymptotically vanishing, well, what I mean by that is whatever C3 norm of the potential goes to 0 as the spatial coordinate goes to infinity, then you have both you have global mixing, and in case the potential is small everywhere, not just at infinity, then you also have local global mixing. Okay, so there is a big difference between these two statements. One of them is requires that the potential is small at infinity. The other one requires that the potential is small everywhere. There is results for Galton board, and there is results for certain ping pong maps. So in case of ping pong maps, well, here I'm really very hand-waving. There are, of course, a lot of conditions. For instance, if you look at this paper, there are some conditions under which the ping pong map can be well approximated by a periodic map at infinity. Okay, so this is exactly the kind of setup where I want to use this theorem. And yes, you can do that. And because of this paper, essentially, you can, and because of previous theorem, you can conclude the global mixing for both map and flow. Okay? But in this generality, the local global mixing is not likely to be true because you could have some elliptic islands, for instance, for small energy, and that kind of spoils local global mixing. Maybe if you impose some extra conditions, well, if you impose some extra conditions, then you hope that the system is ergodic and recurrent, and then you have some hope to local global mixing. But you necessarily need some extra assumptions. And there is another very recent work by bouncing was similar to the Fermi-Lamb, but it's somewhat different because the flight is unbounded above, and then basically if the energy is large, then it takes a lot of time to come back, and that kind of spoils the global mixing for the flow, but you still have global mixing for the map. Okay. So maybe if you allow me just one more remark without writing anything more on the blackboard, that maybe another thing that we are looking at now together with Marco is some Birkhoff theorem for these spaces GO and GU. Okay, so in the previous talk, there was, what was that? Random walk in deterministic environment, okay? You could have a deterministic walk in a random environment, or sorry, maybe I confuse up things. So there was a deterministic walk in random environment. So here you can have a random walk in a deterministic environment. So in case your observables, so these values of the function phi, and sorry, where is phi? The values of the phi are IID, okay? Then the Birkhoff theorem would be, in other words, called random walk in random scenery, if you are familiar with this term. You have a random walk, and you have an IID environment, and you count each time you go to a place, you add it to a sum. So you consider the Birkhoff sum for this infinite measure preserving system of this observable, which is IID. This is called a random walk in random scenery. And we have some results, in particular, if you are in space GU, then you have strong law of large numbers, so the strong version of the Birkhoff theorem holds. If you are in GO, then you have a weak law of large numbers, but you do not have a strong law of large numbers. There is counterexamples. So probably you want to shoot for something in between, and we have something in between. So if you have an estimate on the speed of this convergence in terms of the volume, then you can, for instance, recover the IID environment. For IID environment, the speed of convergence here would be volume to the power 1/2, right? Just the central limit theorem for IID environment. And for that case, we have a Kasten-Spitzer theorem that the typical scaling is n to the 3/4 in dimension 1. Okay. So for these kind of much bigger spaces, when we impose this extra condition that on the speed of convergence to be volume to the power 1/2, we can recover this power 3/4. So I would say it is an extension of the Kasten-Spitzer theorem. Well, we do not have a limit theorem. We just have a theorem that n to the 3/2. If you divide the Birkhoff sum by n to the 3/4 plus epsilon, then you go to 0 almost surely. Okay. So this is the kind of result that we are looking at now, and I find it quite interesting that you can say something for the Birkhoff theorem in this kind of big classes of functions. It's a huge generalization of the IID. It's not just IID; it's much more to it. Okay, I think I'm running out of time, so I'm stopping here, and thank you for your attention.
Questions?
Can you come back to the theorem where you said that you didn't need to say anything about the group? I don't know if it was.
Well, I said something about the roof. Which theorem?
It was
Z extension?
Yeah, it was before.
Sorry, maybe next one? Sorry, which one?
It was before the global mixing.
Before the global mixing,
yes.
Okay. This one?
again before? It was for...
Okay, so this is theorem 4, so I go back to theorem 3. This one?
Okay, I don't remember. But with the kappa.
Well, that was the global, I think.
Okay.
This one?
Okay. So you say you don't need to say anything about the group, but what if kappa is equal to 0, say? Does it fit in your setting?
Well, I say satisfies the MLLT.
Well, kappa equals 0 satisfies the MLLT with group 0, which is a discrete subgroup.
Well, the MLLT is, the MLLT kind of implicit limit is non-degenerate. So there is, a convergence to something like a Gaussian density. Or if you have kappa equals 0, then you don't have the convergence to Gaussian density.
Okay, so in your definition of MLLT, you exclude the case where you have...
Well, I try to exclude the case.
Okay.
So the definition was, well, there are various definitions related to one another, right? But the definition that I gave is that it converges to a limit where the Gaussian density was there. So maybe I should have said sigma is positive. That's what...
I don't know.
Well, I mean sigma is positive.
Okay.
Right. So the degenerate case is not considered.
Okay. Thank you.
So maybe we are going to discuss after, because we have just 3 minutes.
Yes.
And so let us thank the speaker again.